Welcome back, everybody. Welcome back to the channel. So, I've been gone for a minute. I'm in a new place now. I ended up moving to a new location, so that's kind of why I just haven't been doing videos. It was just entirely too hectic for me to do videos last week, so I apologize. But with me being in a new place, before we get started on the video today, I just want to make a quick announcement. We're getting pretty close towards the portion where we're pretty much about to finish the development of the virtual machine and start actually working on doing the compiler side. So if you guys remember this picture that I made for you guys a while ago, if I zoom in here, you can see that, oh, it's taking quite a while. That's kind of weird. But you can kind of see that here's like a general graph of how much lines of code relative to how long it takes to actually develop things. And we're kind of at this point now where we're pretty much finishing up the virtual machine and we're slowly going to start coming up this little hill here and, basically finishing up the compiler and then making everything all work together. So that's pretty exciting. I actually didn't think we'd get this far this fast. I thought it would maybe taken a lot longer. But before we actually get to the compiler, I think that it might be a great time now that I have a decent amount of subscribers. I'm also thinking of doing a live video on Friday as well. So I'm projecting to do it roughly around 6 o'clock p.m. Now, I've never done a live stream before, so it's going to be probably a hot mess. So keep that in mind. Also, too, if that doesn't work for you guys, let me know in the comment section below, and let me know what times may be better for you. Like I said, I'm going to be doing 6 p.m. Central Standard Time. So maybe if there's a different time that might work better, then just let me know, and I'll try to, of course, pick the best time that works for you guys. So with that out of the way, let's actually get into what we're going to be talking about today. So today we're going to be talking about the main execution loop. This is going to be pretty much the heart of your programming language. Like we're now at the heart of where basically everything runs, and we'll just kind of go through it. So I don't want this video to be too long because it can get really ridiculous. To be honest, in all honesty, this is just a bunch of tedious tasks, a bunch of tedious code. And I'm not going to go through every single instruction today because I've already gone over every single instruction already. And I've already explained, what each instruction does and why I have it. So I'm going to put that in the description below if you want to check out that video, which will kind of go over that. But instead, what I'm going to do is talk a little bit more high level and go through a couple of instructions to show you guys some things that you might want to think about as you're building your main loop. So what you want to do is, if you haven't already, create the execution or exec function. Just basically create a function where you can execute your code. Now, personally, I would actually have mine inside of the threading object. That way you have direct access to all of the various fields inside of your thread object. So that's kind of what I did. So that way if I want to access, any of these fields in here, and there's tons of fields, of course, that you need to access. Otherwise, another potential way you could do it is just, of course, pass in as a parameter. So then you could just do it that way. But once you do that, you want to create a couple different variables here. So as you can see, I have a couple different variables. They're all going to be used for different things. Now, there's something very important that I want to mention before we go on with the actual instructions. The way that I access data in my programming language is I use a pointer system. So if you guys remember a while back, I talked about it in a previous video where I was talking about how objects are actually created and how the structure of each sharp object is made in my programming language. And I mentioned that each sharp object has what's called a object container. And the object container is this thing that you see here, this data structure. And each container has a sharp object, which is, of course, managed by the garbage collector. As we're accessing objects, if I scroll up here to the top, we can see here that we have two types. So we have a union inside of this sharp object, and that represents depending on what type of data we have. So if we just have a number, it's going to be just an array of doubles, and we can just access that numeric value at that index inside of that data structure, and that works just fine. However, if this is a data structure, then what we're going to do is have an array of objects or array of containers, So that way we can again detach ourselves from the actual sharp object system, and the garbage collector can continue to manage those objects. And then we want to move the node to what object we're pointing to. So a basic way to understand this is if we want to access a local variable, let's say in our programming language we want to access this pointer variable, we would call the instruction move local, and then what would this be? This would be 0, 1, 2, 3, 4. So this will be 4. And the reason why it's 4 is because every single function, the way it's going to work, and I've mentioned this before, whenever you have an instance function, the first element in that function is always going to be the instance of the class. And then anything after that is going to be the address of each field. So we start out as index 0, then 1, 2, 3, and then 4. So that's how we get that number. So you'd access it, and again, we're going to see these instructions below when we kind of go through it, so we'll go over this a little bit again. So you say move local 4, and then let's say we want to access a field inside of here. So let's say this object that we're pointing to is actually a thread object in our programming language. Well, the way that we do that is we would say move local 4 and then move node and then whatever field we want to access. So to make this easy, I'm not going to pick a far down field. So I'm going to pick the first field in the actual thread object. So let's pretend that this is actually in our programming language. We would say move node of 0 because that's where the index of the calls field is. And then that would allow us, move node of 0, to access the calls field. So that's kind of how I do it. So that's kind of the basic system. So keep that in mind as we're going through this. Now, I'm going to skip over the profiler code. I'm just going to let you guys figure out your own profiler source code. I'm not going to go over that because it's just very messy. I just don't really like the system. Plus, I'm going to be ripping it out and changing it anyway, so I think it's pointless to show you guys. But now we're in the actual main execution loop. So what you're going to want to do is first initialize your opcode table. Now, I think we've gone over this, but let's just go over it again. So it's going to be a static array of just basically addresses. Now, here's how you do it in GCC. GCC is the compiler that I actually use to compile this code, and the format works as follows. So you have two ands, the name of the label, and a comma, and of course, because this is in a header file, you have to have these little slashes. So just create that. Now, I'm not going to go through all of them. It's pretty self-explanatory. Whatever instructions you guys are going to create in your own programming language, of course, you're just going to want to create your opcode table and have each of those values. Now, you want to be absolutely sure that when you build this opcode table, you want to match each of these values with your actual instructions. Because if I scroll down here to the opcode data structure, you can see here that I have no op as a value of 0. So that way when I access or jump to the next instruction in the opcode table, I'm going to jump to index of 0, which corresponds to the no op instruction. So please make sure that you keep that in line with your numeric values down here. Of course, if you have any trouble or if you want to take one of these values out, then you can always scroll down and find in the opcode.h source file a quick and easy way to basically generate a bunch of hex numeric values. So that way you can just literally copy and paste the code and not have any issues. You can just copy and paste the numbers in. So if I go back now, you want to surround it in a try catch and then an infinite for loop. I have it surrounded in a try catch because there's potential that some of these instructions actually do throw a physical exception. Now, here's where we get into some really cool things. Now, this is kind of what I use on a day-to-day as I'm debugging my programming language. So let's say I go here to my ODF file, and let's say I go to the main method. So I'm going to do a search here for the main method. And in the main method, you can see here that I have a bunch of instructions that I'm executing. Let's say that the instruction of number 2, there's a problem with that. Let's say for whatever reason I'm getting a seg fault at instruction 2. Now this is again going to be dependent on your programming language, but this is something that I use to debug and fix bugs in a rapid fashion in my actual programming language. So what I do is I literally just put a breakpoint right here inside this if statement, and you have to put something in there, otherwise it'll just skip over it as you're debugging. And I check to see if the current function that is a field inside of our current thread object, which is going to be set every time we execute a method. I check to see if that address matches, the address of whatever function that I want to call. So in this example, the address is 3045. So 3045, and then I say PC is greater than or equal to 3. Now, the cool thing about this is that you can literally make it whatever you want. You can say, as long as we are greater than or equal to 3, which means any instruction after this, we want to debug and run into the breakpoint on that instruction as we're executing our code. You can also segment it to where you can only look for instructions between 3 and let's say 10. And yeah, so that's really cool. And the way that I do that is I do what's called a dispatch. Now, dispatching basically is a way for me to jump to each instruction. Now, whenever I call dispatch, that is controlled by BRH no increment, and we'll see this in a second. But basically, the way that I debug it is I say go to top. And I do that, whoops. So I say go to top, and literally top is an actual label here, and you can see it's getting highlighted now. And now, basically, after every single instruction, I'm going to call BRH, which then calls BRH no increment. And every time I execute an instruction, I basically branch, that's what BRH stands for. I increment the PC based on whatever I pass in here. And then I call BRH no increment, which checks to see if we have, of course, any signals. So any exceptions, suspension, or kill. And then I either dispatch or go to top. Now, when I'm debugging, I'll just put in this go to top code, which will then subsequently take me to the top of the main loop, and then I'll just hit this breakpoint if the criteria follows. And again, this is a great way to do that to test your programming language. So once you do that, then once you kind of test it, I recommend not doing that or not doing the go to top, because it does slow it down. What you actually want is you want to jump from instruction to instruction. You do not want to be bouncing around unnecessarily, because at the processor level, the more branches you end up having, the slower your programming language is going to be. So you want to have the least amount of branches inside of your main execution loop as humanly possible. So keep that in mind. So once we do that, then we just have our various instructions. So first we're going to have no op. This is pretty self-explanatory. Next, we're going to have int. Now, this is the cornerstone of my programming language, and it's honestly going to be the main, most important instruction in your programming language as well. When you're starting out your programming language, you're not going to be as advanced as my programming language initially. This is what I used before I had the Sharp Native Bridge for several years. What it does is it allows us to do a wide range of tasks at the very low level. So we can do stuff like printing stuff to stack in a formatted fashion. We can also get the time, do some garbage collection control. We can also do some multi-threading control as well, and just tons of other stuff, messing with files. Basically, I'm not going to go through this entire function. If you guys are curious about it, you can check it out. It is called System Interrupt in the virtual machine.cpp. You can simply just do a search for it. And if you want, you can just copy down all of the various things that I do. And I actually have a file called interrupt flag where you can actually just go through and see all the various different things that I'm doing at the low level in my programming language. Now, I will say you don't want to put too much crap in the system interrupt. At some point, you are going to need to build a bridge between your programming language and C++, because the more crap you put inside of this function, that means the larger your executable is going to be, because you have to write all of this source code. I ended up creating a folder that contains a lot of this source code. It is located in the lib modules, and each module representing the high-level name of each module has its corresponding C++ code that corresponds to whatever I need to do. So obviously, if I'm, doing IO stuff for files, I have a few CPP files for doing file manipulation, and of course, memory management as well. And I also have stuff for random number generation and math. So again, the more stuff that you put inside of here, the bigger your file is going to be. So definitely keep that in mind. After that, I do a check to see if the VM state is actually terminated. Now, this is a language specific thing. You may not need to do this. The only reason I'm doing this check is because I actually have source code inside of the system interrupt that could potentially shut down the entire programming language. So that's why I need to do the check. Now I'm going to skip over movi. Movi is just a basic way for you to set an integer value to a register. And here's an example where we can see a dynamic branch increment. So I'm incrementing the program counter to 2 instructions. This is going to be a perfect example of what I called overflow instructions a while back. Basically, these are instructions that are so large that we need actually 2 instructions to contain all of the information for that instruction because it's just too big to fit inside of one instruction. So that's how I do that for those. And as far as returning a function, function returns are going to be very interesting in my programming language. So this is kind of getting into the exception system, which I'm still holding off on the exception system because it's pretty complicated and, to be honest, a little confusing. So in short, basically what I do is every time you return out of a function, I check to see if we're in what's called an error state. An error state is just a Boolean, or it's a number, and if the value is, whoops, if the value of the error state is 1, then that means that we're in an error state. We set the exception object to whatever is on the stack. And then we basically pop it off the stack and we return the method. Now, I don't think I've gone over returning methods before, but let's just go over it. It's very simple, guys. Literally, the way I return methods is if we're on the last method, I return true. And if true is returned, then that just means I need to bounce out of the main execution loop because basically what that means is we're at the end of the road. So obviously, as we're executing our source code, we're going to jump into this function. Once we get out of the last function, we just return out of here and the thread finishes. But let me go back. After that, I literally just get the data off the frame, and the calls variable is pointing to the most recent frame that we're pointing to based on how many function calls we've made so far. And I just set the current function to whatever the return address was for that frame. And again, the frame is representing a actual function call that holds all the necessary information for us to return back to the previous function that we once were residing in. So it literally just sets those values back to its old value. I decrement calls, and then I also return at the very end whether or not we're in JIT mode. This is extremely important because the JIT mode is going to be set to true if we are calling a function that is either in fact a JIT function or we're calling a C++ function at the low level. We'll see a little bit more of how this is JIT works with the sharp native bridge later on, so we'll see that, but that's pretty much what we do. And if so, if it's time to return, we check to see if the result is equal to error state. We set the signal to a tsig except, meaning that we have an exception signal, and then we just return out of this function. Now, if we get down to here, meaning that we are not at the last function, we check to see if the current result is equal to an error state. And if so, then we send an exception signal and we jump to exception catch. Now, I try not to throw physical exceptions wherever possible in the programming language as we're running through the main loop because it just slows things down. It's a lot easier to just jump to an address than to actually throw a native C++ exception. Now, here's an example also of doing a long call. Long calls basically represent, if you guys remember, this is a way for us to keep track of how many times we've bounced around into a function so that way we can actually JIT the function. So if you guys remember, the JIT IR limit is 25,000. So if we've either called the function 25,000 times or ran a for loop inside of the function more than 25,000 times, then we increment the branches, and yeah, so that's one way. Now I litter this in a couple different spots. So if I return out of a function, if I call a function, if I branch around, then I will call this long call. So you guys can, put that code wherever you want. That way you can keep track of it so your JIT can respond accordingly. Of course, you can always come up with your own rules as well for your own JIT. So Keep that in mind. Also, we have Halt. This is just a quick way to kill a thread. This does not shut down the entire system. Here's an example of actually how I create a new array. Now, we've already gone over creating objects in the programming language, so I'm not going to go into that function, but basically I increase the stack and then I set the container equal to whatever the sharp object that is passed. That is going to call this operator equals on the actual object container, and of course we will decrement the reference if we have one, and then we'll assign the new value and increment the reference if possible. Now, one thing I want you guys to know, so as we're setting this stack element object here, before we actually set this object, what we want to do is we want to do a stack check beforehand. Previously, what I was doing is I was actually doing a stack check after the fact, which is actually pretty bad. So what I do is in the stack check, I basically take the stack pointer and I increment it one time, and I do stack pointer minus data stack, which gives me the actual physical numeric value of where we are in the stack. Because remember, the stack pointer is actually a pointer to the physical stack element in memory. So if we take stack pointer and subtract that to data stack, that gives us the actual number. And if we increment that and that's greater than the stack limit, then we have a stack overflow exception. And that's how you get stack overflow exceptions in the actual programming language. Now, these things are rare. You typically don't get them when you're newing up objects. It's typically when you are calling a bunch of functions and you just call an indefinite amount. After that, we also have object casting. Object casting is going to work a little bit similar to how the compiler is going to work at the high level. So we basically say we want to try to cast to a class pointer. Now, this is going to be in the actual container object, and that way we can just physically access the object value or the sharp object that we want to cast to. So what we do is we get the physical class object from the class's array inside of the virtual machine that we created when we read our executable. So that's going to be in the virtual machine object, and we'll access that array. And of course, we want to make sure that you don't go out of bounds. So you want to make sure you do a bounds check on that, and once you get that, then we basically check to see if the current object itself is in fact a class. So I do a check, and what that does is that just looks at the info of the actual object and it checks to see if that bit is enabled. And if that bit is enabled, then we are good to go. Otherwise, of course, you can throw a class cast exception, and you'll basically just say attempt to perform invalid cast of whatever, and you want to print out the actual class that you were trying to cast to. And now here's an example. I actually do throw a physical exception because I want to just backtrack the actual code instead of having to do some weird stuff. And basically, every time when I throw an exception, I create this exception object and I literally push the exception onto the stack. So what this source code does is we basically want to check to see if we have an out of memory exception as we're pushing it onto the stack, because obviously if you have an out of memory exception, you can't create new stuff because you're just going to get another out of memory exception. So what I do is I basically just guard the thread's mutex. I say the thread is killed if it's an out of memory exception. I set the exception object, and then I basically fill up the stack trace on the actual stack trace field. That's going to be located inside of the actual support library. So if I go here to, where is it at? It is exceptions.sharp. And you can see here that I have this message, which is a string array or an int 8 or a char array. And then I have this stack trace, which represents an actual string. So after I resolve the field, then I create a new object unsafe. And what this new object unsafe does is it allocates a object without getting out of memory exception as a result of calling the custom malloc that I created above. And it still adds it to the garbage collector, so it's still going to get freed up as normal, because just because this one thread died doesn't mean that the programming language is dead. That just means that maybe this is thread 3 and we have maybe 2 other threads that potentially could be running, and those will be just fine and unaffected. So you just want to make sure that we add that to the garbage collector so we can process it properly. And once I do that, then I kill the thread and that's it. Now, if it's not an out of memory exception, then I basically set the exception object to the handling class of the throwable, so I can pass in every time I create an exception the actual pointer to the class object, which is going to be referenced to one of the objects in the virtual machine. So if I go back to my virtual machine, you can see here that I have these frequently used classes. So I can pass in, a Stack Overflow exception, index out of bounds exception, and more. And then when I do that, I can actually use that physical class to create a new object and then set the appropriate fields to be handled later on. So that's kind of how that works. After that, so if I go back into casting, so the way that I cast objects at the low level with my programming language is obviously if the object that we're trying to cast is the object that it is, then no biggie. Otherwise, we check to see if the class is related. Now, if you guys remember, every single object can go all the way up to object, basically. So if I go to the actual object class in my programming language, the object class represents the highest level class that every object in the programming language is going to stem from. So this would always be the last class that we stop at as the superclass. And if that's not true, then we're going to go a little further by checking to see if the class we're trying to cast to is in fact an interface and if we have access to that interface. So that's pretty much it for that. And let's go on. So if we go back to the main execution loop, I have a bunch of casting stuff. This is pretty self-explanatory. You just basically cast a number to another number. Again, this is another example of pushing data onto the stack. So this pushes a numeric value onto the stack based on whatever is inside of a register. And of course, we check the stack beforehand. So if I keep going down, I also want to add training wheels to your programming language. So let's see if I can actually find an example of this. So here is an example here. So, and also before I get to that, this is how I call functions at the low level in my programming language. It's exactly the same way we just went over before. Nothing changes. The only difference is there is a label value here. So all of the stuff that I talked about for calling the main method applies here. Call D is another way of how I call functions in the programming language. It's just a dynamic way of doing it. One thing that you're going to want to start to think of as you're building your programming language is static code and dynamic code. Static code basically represents anything that's burned or etched into the actual executable, basically meaning that it cannot change as the program runs, right? So if you say, I want to call function 11, well, once your virtual machine reads in that executable, it's always going to call function 11. So it's not going to be able to dynamically change based on some circumstance or situation. So you just want to make sure you have a decent balance of static instructions that will execute static code and dynamic instructions like call D that can change based on the situation. So think of that. Now here's an example of training wheels. I still have these training wheels, and this language is like 5 years old, so I think that says a lot. They probably will be coming off pretty soon, but basically, as you're building your programming language, you're going to be running a lot of code. But basically, what you want to do is like in very specific instructions where you're doing things that potentially give you a seg fault, like accessing an array at a specific index, you just want to make sure that you're not doing any weird things. So if the node that I'm trying to access for accessing a data structure is outside of the bounds of that physical data structure, then I'll just say new exception move node, and I'm writing in the instruction that crashed. So I'm not really giving too much detail here because again, it's training wheels. It's not designed for me to be very descriptive because in all honesty, this exception shouldn't be happening. If it happens, that means that I have a bug in my compiler that I need to fix immediately. Also, another thing that I want to mention is I have these catch-all safety checks, and they're just a bunch of defined statements, and they all do different things. Basically, it's a way for me to write safe code, so that way I can ensure that nothing weird happens if something does happen. So basically what I do is I have these check nulls, which checks to see in general if the object that we're trying to access is null. So if you guys remember, we're accessing the pointer field. So I'm checking to see if the pointer is equal to null or the pointer object is equal to null, because again, both the container and the container's value could potentially be null. So we just want to make sure that that's the case. I also do some other checks in here to see, like, check null object. If the object is in fact not a data structure, then I'm going to give an exception. And again, I'm not throwing physical exceptions because that's expensive. I'm just building an exception object of null pointer exception, which, remember, it's going to just basically create that object, pass it the information based on the message that I have here, and then push that data onto the stack. And then I'm just going to send the signal of exception and then go to exception catch, and the exception handler will handle that exception. So if I go back, that's just a really nice way, if any of you are wondering what that is. It's a very quick way to make sure your code doesn't break. It's another form of training wheels. Honestly, you shouldn't have to do that, but you know. Now, to be honest, I'm probably never going to remove that. I will probably remove like these if statements, but these check nulls, I don't ever think I'm going to remove it, because in my opinion, at the end of the day, the goal of your programming language is not to run it in the main execution loop. The goal of your programming language is to actually run it in the JIT mode or in C++ mode. You want to basically transition your programming language to run as close to the metal as possible, because doing this high level crap is just really slow. After that, I think that's pretty much it. I mean, here's an example of, like, for instance, a hard instruction. So I forget what I called it, a static instruction where basically it's not dynamic. So I'm skipping over a specified amount of instructions based on whatever I passed here. If I want to change this, I'm going to have to recompile the source code. So keep that in mind. And here's an example of like an if statement. So skipping over a specific amount of instructions if this value is equal to true. Now I have two different concepts in my programming language. I have skipping and I have if statements. So skipping are for inline if statements, and I also use this for just general if statements as well. It's very confusing. Don't worry, we will talk about this later. I'm not going to explain it now because there's no point. This is literally something that we're going to run into as we're building our compiler, and it'll just make more sense if I wait to talk about it then. But just know that this is for if statements. Here's an example of how I throw an exception in my programming language. I basically just set the exception object to whatever is on the stack. I pop that value off, I send the exception signal, and jump to exception catch. Here's how I check to see if an object is equal to null. So that's how I do null checks in the programming language. Now, also another thing that I want to mention is returning data. Now, I know I've mentioned this before, but I want to mention again. When I return data, the way how it works is if I have a function, whoops. So if I have a function that has two values, let's say I have an x and a y. And these are two fields that we're going to pass in. Let's say x has a value of 1, y has a value of 2. And we want to basically add x plus y and return that value. Well, in order for us to return 3, what we're going to have to do is basically set x to the value of 3. Now, if this is a static function, then we'll just set x. Otherwise, what we'll do is we'll have x plus y. We'll also have the instance as the first field in the actual function. So we'll end up setting the instance to 3. Now, I know some of you are wondering, well, how is that possible if we have a function where we have x and y, and we're adding these values and setting x to 3 as the result? You'll see later on, it's actually not that difficult. It's just a matter of timing and making sure that you order your instructions in the appropriate way so you don't have instructions stepping on each other's toes. So we'll see that later on as we build our compiler. But that's pretty much it. Here's another training wheels example. That's for accessing integers. Let's see, is there anything else before? Yeah, so that's pretty much it. Here's an example also too of how I access thread local variables. So this is a TLS move local, and what it allows you to do is just access a thread local's value by just accessing the data stack, and we just get the physical thread local's address. So that's gonna be it for today, guys. Hope you guys enjoyed the video. As usual, if you have any questions, as always, put them in the comment section below. And of course, you could always send me an email. That's going to be in the description below. And again, remember, I am doing I'm looking to do a live stream this Friday, so definitely watch out for that video. It's going to be pretty informal, so I'm probably just going to be programming the drone project, to be honest. There isn't really much I want to do on the language side right now. Also, if you guys would love to help support the channel, you can always head over to the GitHub repository at androidevcd/sharp. When you do, definitely watch, star, and fork this repository. It gives this language a lot more visibility and let other developers know this language exists. Also, if you guys are curious about some of the things that I'm looking to do in the future, or some stuff that I've already done, or even stuff that I've done in the past, you can always head over to the roadmap section. This is a nice, real-time, live way for you to see what's going on with the programming language, and I have some pretty decent descriptions explaining some of the various things that I'm working on. So that's going to be it for today, guys. As usual, if you guys are new to the channel, definitely consider subscribing, and until next time, I'll see you guys later.